Hello, and welcome, folks. Today, we're excited to have a guest speaker here in our course. It's my pleasure to introduce Tsung-Wei at the University of Wisconsin. He recently is actually also at the University of Utah and has moved over. He's done a number of things, and actually, we're going to hear about two of them in this talk, right? In particular, Taskflow, which is a fantastic parallel programming interface and library. And he used that and to create OpenTimer, a widely used static timing analysis tool. And I'm happy to have this as a very timely lecture because just on Wednesday we covered a very basic STA overview. And so hopefully everybody's ready for that. Perfect.
Okay. Should I get started?
Yes, please.
All right. So thank you for the opportunity. Today I'm going to talk about Taskflow. It's a general purpose task parallel programming system to help you simplify parallel computing and programming. And here's what I'm going to do in today's talk. I'm going to first briefly talk about how to express your parallelism in the right way. And then I'll introduce how to use Taskflow to program both static and dynamic task graph parallelism. And next, I'm going to show you how we overcome some of the scheduling challenges when we build a system. And I will demonstrate the efficiency of Taskflow from a real-world static timing analysis application as an example. And then I will conclude the talk. So during the presentation, if you have any question, feel free to just post the question on the chat box, and I will answer that in a minute. So you probably already know parallel computing has advanced many of our application performance to a new level that is previously out of reach. Take a very important static timing analysis application, for example. With multi-core parallelism, we are able to reduce the time by several orders of magnitude. And even with the GPU, we can bring another 10 to 100x speed up to the static timing analysis applications. But, today's parallel computing applications are actually not very simple. So here I'm showing you a computational task graph of a GPU accelerated circuit simulation workload. So the task graph model over here, we have modeled a GPU operation in a node and a dependency between GPU operation in an edge. And as you can see, this computational task graph can be actually very, very huge. So in this example, we are analyzing and simulating an NVIDIA design of up to 500 million gates. It has over 100 kernel and dependencies. Even with a GPU, it is going to take over 500 seconds to finish. The total turnaround time is actually very, very long. So it turns out writing a program that utilizes the parallel computing resources is not a very easy task because we have to deal with a lot of technical details, such as abstraction over the software, hardware, concurrency control, cache and data race avoidance, or you have to build a dependency constraint. And you also need to worry about the scheduling efficiency, load balancing, and so on and so forth. And there is always this trade-off between, what you really want and the cost of that design. For example, I'm pretty sure everybody wants a simple, maintainable, extensible, and portable implementation, right? But each of that design will steal a little bit performance from your application. And I do believe nobody wants to touch too many details themselves. So we want a high-level programming solution that can help us handle all these technical details because from applications perspective, they really care how fast they can get things done. And from users' perspective, the biggest challenge is always the transparency, right? Whether it is over parallelism abstraction, runtime optimization, or load balancing, and so on and so forth. And from the evolution of parallel programming standard, we can see that task parallelism turns out to be one of the best models for the future parallel computing architectures because it can capture your intention in decomposing a parallel algorithm into a top-down task graph. And they can scale to a larger number of different processing units, such as CPU, GPU, and some other emerging accelerators. And that is why, over the past few years, we've seen many different task graph programming models, such as OpenMP, StarPU, and Cocos from the Department of Energy, and TDP from Intel, Parsec, and Fastflow, and so on and so forth. So even though many of these existing systems have demonstrated certain success in certain application area, And when we are trying to use it to parallelize our application in computer-aided design or EDA, we realize two major issues for existing systems. So first of all, they cannot handle very efficiently the workload that has very, very complicated task dependencies. For example, if you look at a circuit analysis algorithm, usually we have to compute the circuit network of a very big circuit graph that has millions of nodes and dependencies. And the problem is existing tools, they are often very good at loop parallelism, which is the ability for you to express parallel independent iteration in a loop-based fashion. But they are not very strong in expressing a task graph at a larger scale with the more irregularity. So that's the first problem of existing system. And the second problem is they cannot handle efficiently the workload that has complicated control flow. Right? So if you look at many of these circuit optimization, circuit synthesis algorithm, we essentially make a lot of use of dynamic control flow to implement multiple patterns such as combinatorial optimization, graph algorithms, discrete math, or analytical methods such as physical synthesis, placement, and so on and so forth. And the problem is, if you look at existing tool, the way they model the computational patterns is they are very good at static task graph parallelism, but they are not very strong in expressing dynamic, task parallelism that depends on runtime values. And frequently they base on the direct acidic graph model that does not allow you to express, for example, iterative control flow or some other more dynamic, more complicated control flow decision in your graph. So to solve all these challenges, we are going to talk about how our system Taskflow can help you program static task graph parallelism. So we have introduced a new task graph programming system called Taskflow, and let's take a look at a static task graph example, the so-called hello world example in Taskflow. So suppose you want to build a task graph that has 4 tasks, A, B, C, D. A has to run before B and C, and D needs to run after B and C. Okay, so when A finishes, B and C can run in parallel. When both B and C finish, D can start. Okay, and this is how it looks by using our system to describe a computational task graph. So first, you create a Taskflow object, and then you create an executor that manages a set of worker threads to schedule your task graph. Then you can in place 4 tasks in terms of C++ lambda function object or other general callable object in C++. Then once you have the task, you can use the precede method or the succeed method to relay the dependency between different tasks. For example, A has to precede B and C, and D will need to run succeed B and C. Finally, you can submit your task flow to the executor, and the executor will perform all the scheduling details to optimize your parallel execution of your program. And at this moment, I believe most of you can fully understand what this code is doing. It is very, very expressive and it's very transparent. All you have to do is to think about how you can convert your application into a task flow graph. And you don't have to worry about all the scheduling detail. So integrating Taskflow to your application, to your project is fairly easy. It's a drop-in integration. So Taskflow, the project itself is completely header file only. So that means you don't have to worry about installation. All you have to do is to copy the Taskflow project to your local directory, and then you can compile your program by telling your compiler where to find the Taskflow header file, and that's it. You don't have to pre-compile or pre-build the Taskflow into a static or shared library, so you don't have to wrangle with all those tricky installation details. And we also have a very lightweight profiler. It's built in. All the Taskflow program by default can be profiled, and you can visualize your execution results by running your program with this environment variable enabled. And the Taskflow runtime will generate the profile data in a JSON file, and then you can simply copy the content from the output and paste it to our web-based interface that you can visualize the execution timeline of your program. So now I'm going to talk about a key innovation that separates Taskflow from existing system, and that is our control Taskflow graph programming model, or CTFG. So CTFG goes beyond the limitation of existing DAG-based model, the red acidic graph-based model, that does not allow you to express control flow in a single graph entity. For complicated example like this, where I have, for example, 3 control flow that I have to describe an iterative control flow over here, or conditional tasking, if else, decision making over here, or another iterative control flow over here, it becomes very difficult for existing DAG-based system to express an efficient overlap between your task and control flow, right? Because they do not anticipate cycle. In that case, you are not able to express iterative control flow. So in Taskflow, our programming model give you a very, very simple interface that you can just return a value that tells us, the scheduler, which task you are going to perform, which task you are going to schedule. For example, if you look at a condition task over here, condition task number 2 over here, it precedes a task G and another task H in the index 0 and 1. So when you return 0 from condition task 2, it actually tells the scheduler to run task G. And when it returns 1, it will tell the scheduler to run task H. So this conditional tasking interface can actually handle very, very complicated scenarios, such as nested or non-deterministic control flow, right? In many of these EDA optimization flow, we have a lot of stochastic optimization. A lot of time, the decision-making is totally random. The decision-making follows a stochastic probabilistic framework. So Taskflow actually has the conditional test interface we have actually can help you solve this challenge to model your tasking together with non-deterministic control flow in a single graph entity. So in this example, I have a task graph of 5 nested cycles. So each green task is a condition task. It flips a binary point to decide the next path by returning a binary random binary value. So if a return value is 0, it will move on to the next task. If the return value is 1, then it will go back to the first condition task. And there are a total of 5 condition tasks. Right? Each condition task will return a binary, random binary value to decide the next task to run. So you can already infer that in order to finish the execution of this task flow graph, we have an average about 32 tasks to go through before we can finish the execution. But ultimately, we only need 1, 2, 3, 4, 5 condition tasks to model this non-deterministic control flow. So how does existing framework handle control flow? We know most of the existing framework, they are not very good at handle workload that has dynamic or nested or even complicated control flow decision-making point. If your task program or task graph happen to have a fixed length iteration, happen to run across a fixed length iteration, then the simple solution is you can unroll the task graph by, for example, 5 iteration or 10 iteration, right? But the problem with this is, of course, the task graph size will become very, very large. But what about a control flow that has unknown or non-deterministic iterations, right? Or some situation may have very, very dynamic control flow that runs decision-making on the fly, or depending on another control flow, and so on and so forth. And there is no way, literally no way for you to leverage existing task parallel programming system to handle this scenario. Very often, you might end up with client-side partition around a decision-making point. For example, if I have an iterative control flow like this, then without using Taskflow, one simple way is you have to partition your Taskflow graph around the decision-making point, such as the task Y over here. and then you run multiple partition task graph individually. And the result of this is, the downside of this is you have a lot of synchronization overhead. And in fact, similar problems have also been studied in existing large-scale machine learning systems, such as the TensorFlow, FlexFlow, DGL by Amazon, and so on and so forth. Okay. So now I'm going to talk about another important feature of our system, that is a composability. This is very, very important for expressing larger scale parallel workload, but really supported by existing tool. So you can create multiple task flows, each representing a partition of your parallel decomposition strategy. They are easier to optimize at a smaller scale. Then you can assemble this partition task flow into a large task flow graph, and they compose correctly and efficiently. For example, here I have two task flows, F2 and M1. And F2 is composed of a module task that describe another task flow in M1. And when you run task flow F2, it will start running F2B and F2A, and then it will run this module task to start the execution of another task flow graph described in M1. And finally, it will stop the execution moving on to F2C. So this is how the interface we define to express composition. So everything is composable in task flow, task dependency control flow. They are all associated with each other to represent a very generic heterogeneous task graph. And our scheduler will perform the whole graph optimization to efficiently overlap task execution and control flow decision-making point. And that is totally transparent to user, which can largely improve your programming productivity. For example, there's a pause on Rapid, sharing how Taskflow helped the company parallelize their multimedia engine in just a few hours. And the result give a company about 8% performance improvement. Okay, so now I'm going to extend what we have been learning so far to solve a more complicated problem using dynamic task graph parallelism in Taskflow. So far, what we have been learning is static task graph parallelism. And, the static task graph parallelism is static in a way that we have to decide the task graph structure upfront. So the task construction is completely separate from the execution. We have to describe the task flow graph, the task graph structure first, before we submit it to the executor. So that means a lot of time we will have to decouple our task graph parallelism, TGP, from control flows. The task graph structure cannot depend on runtime value or control flow result. Okay? And more importantly, because of this limitation, there is no overlap between task construction and task execution. And this can be a problem when we are dealing with large task graph. And we will talk about that later during the experimental result. For analyzing certain circuit simulation workload, typically the task graph can have multi-millions of tasks and dependencies. And this overlap can bring a significant performance advantage. But it's not available in static task graph parallelism, STGP. So for example, over here, this is a hello example that we just saw a few couple slides ago. We will need to construct the task graph first and then execute the task graph. So the task construction and task execution are completely separate from each other. So this is the one of the limitations of static task graph parallelism, STGP. So let's take a look at some of the example of the STGP. So first is cannot handle control flow driven task graph programming. For example, if your task graph depending on the value of, if you look at this program, depending on the value of A, B, C, I may need to construct a different task graph parallelism, right? If A is true, I may need to build my task graph number 1, or if B is true, then I will need to build another task graph 2, and task graph 2 will need to run after task graph 1, and so on and so forth. So this is the type of task graph parallelism that cannot be efficiently described in static task graph parallelism, because there are just too many task graph structure depending on the control flow result or other runtime variables. Or if you have a situation like this, where some of the task graph structure depends on the property, depends on the result from the previously constructed task flow graph. For example, if the task number is 100 from the task flow G1, I'm going to build up a dependency between G1 and G2 this way. Otherwise, I'm going to create a totally different dependency constraint between G2 and G1 and G3 and so on and so forth. So this is the scenario that cannot be efficiently handled by static task graph parallelism. And this is another example that I'm going to tell you, which is one of the limitations of static task graph parallelism. They do not allow you to overlap task graph construction and task graph execution. So here I am showing you a runtime breakdown of a task parallel circuit analysis algorithm. This, in fact, is a runtime result profile from our OpenTimer static timing analysis tool. And as you can see, we use Taskflow to model the timing propagation algorithm, and it can have up to 10 million tasks and dependencies. And looking at the runtime breakdown, the time we spend on building the graph takes over 50% of the entire runtime. And keep in mind, building the task graph, constructing the task graph is typically done only by a single thread. They cannot be parallel. So this slide shows you the proposed dynamic task graph programming interface that we are trying to overcome this challenge. For the same example, ABCD. So instead of creating a task graph upfront, application can create a task graph on the fly using the method silent dependent async and the dependent async. So when you create a task from a silent dependent async, it will immediately run the task and return the task handle to you. If you use dependent async, that means it will additionally return the future object that allows you to query the execution status on that task, or you can simply use the wait method to wait until the execution finish at the point of the corresponding task. So in this case, I use the dependent async task to create a task D, and that will give me a future object that allows me to synchronize the execution on task D, which means when D finishes its execution, and the whole task graph already will finish. Okay? And every time you create a task, you can specify the dependency using C++ variating parameter pack. And this will allow you to specify arbitrary number of task dependencies that can significantly simplify the programming of dynamic task graph parallelism. And more importantly, if you look at the execution timeline over here, the task construction time can overlap with the task execution time. So compared with the static task graph parallelism, the biggest advantage that we can get from dynamic task graph parallelism is we are able to not just more flexibly express the task graph parallelism on the fly, but also overlap task execution time and task construction time, which in a lot of time, if the task graph is very big, we can actually benefit a lot. Because everything happens dynamically, if you want to describe a dynamic task graph parallelism on the fly, we need a correct topological order. And this is because when you create a task, you need to specify the dependency on the task, right? And all those dependencies has to be created already. So you need a correct topological order. So this is basically very similar to the OpenMP's tasking interface, that you need a correct topological order to describe your dynamic task graph. For example, using this ABCD example we just talked about, we can have one possible topological order, ABCD, to describe the dynamic task graph. Or we can have another topological order, ACBD, to describe the task flow graph dynamically in a different order. And you probably can already imagine if we do not have a correct topological order, such as ADBC in this case, that it will disallow you from expressing the correct dependency, because when you are creating the task B and task C are not created yet, and you have no chance, you have no way to express the dependency from BC to D. So you need a correct topological order. So both silent dependent async and dependent async method will also accept a range of dependent tasks instead of using a C++ parameter pack. We do allow you to dynamically specify a range of tasks. This is useful when the task dependencies are unknown at the programming time. For example, I can create a vector of 4 async tasks, and then I will specify the range of the tasks as a dependency when creating another task. Okay. So do we have any questions so far before we move on to the comparison between our libraries and existing task graph programming approaches?
The questions I have are, I think, are going to be probably answered by your numbers. I'm always very curious about empirical results. I'm sure you have evaluation coming.
Yes. Okay.
Oh, you have a question? Yeah, we have one. Go ahead.
Usually, isn't the problem with very large tasks the sheer number of tasks or the sheer size of the graph? So if you have, let's say, 100 nodes, won't you have to write 100 lines in Taskflow?
If you want to create 100 tasks, and of course you can write 100 lines of Taskflow code, but you can also write a for loop if you are able to create a task in an iterative fashion. That is also possible.
Yeah. So what I was wondering is, does Taskflow have like a metaprogramming generator where you give a task with all the dependencies and it generates the code for you?
So we do not generate a code for you, but we handle the scheduling for you. So you still need to provide a task flow. You still need to describe your application in terms of a task flow graph. And then you give that task flow graph describing your application to our system. Our system will do the scheduling for you. And we'll automatically find, for example, what the right number of thread is at this moment, or how many threads do you need to maximize the scheduling performance, or how to dynamically load or balance the load of the execution. So all these scheduling detail optimization are handled by our system, but you still need to write a task flow program from your application. Okay. All right, so for the same example, if you want to use existing systems such as OpenMP, Cocos, or C++, this is what it may look like. If you want to use, for example, C++ async feature to describe this ABCD other example we just talked about, and you very often will end up with a blocking control because C++ async does not provide you any functionality to express the dependency. And the only way that you can express the dependency is to explicitly synchronize the execution on every async task. For example, you can explicitly synchronize the execution of task A before running a task B, or you explicitly synchronize the execution of A before running C. And of course, the problem with this is you may end up with a deadlock, right? Lots of time if you have a multiple thread that are trying to acquire the same resource in a different order, you can easily run into the deadlock situation. So this is another example that shows you what it may look like if you want to use OpenMP or Cocos to express this very simple task flow graph. In OpenMP, you will need to explicitly define the task dependencies, such as dependencies from A to B, A to C, B to D, and C to D. And then you will use those variables. You have to use those variables explicitly in part of your directive statement of your OpenMP. And the problem of this is if my task graph depends on runtime variables or depends on some other function, the return value from other functions, that I cannot decide all those dependency variable upfront. It becomes very, very difficult for me to express more dynamic task graph powers. Now, if you look at the other system like a Cocos, and this is a system developed by Department of Energy, and it's actually very complicated. You have to define a bunch of task templates and tell the runtime you are going to build on the dependency based on the future objects, so on and so forth. And there is actually more code to follow. So this is another example. Comparing our programming model with the existing library POSAC, and this is a library developed by University of Tennessee. Again, if you look at this code, it has a lot of boilerplate session. For example, to initialize the runtime, and you have to describe the dependency in terms of data, variables, and so on and so forth. It's actually very, very complicated. All right, so now I'm going to quickly summarize some of the limitations of the existing dynamic task graph programming libraries. The number one is when we use those libraries for our application, we found they suffer from very large verbosity, especially from the ease of use standpoint. A lot of time the code does not explain very well itself. And of course, I know this is very subjective when it comes to whether it's easy or difficult to program an application using a library. But most applications only care how fast they can get things done. They will not worry about the performance until they can get their things done fast. So the second limitation we found is many of them count on data flow programming model to express the task dependency. But data flow is a totally different concept from task flow. In our system, we do not handle data because the way you want to handle the data, optimize data, is completely up to your application. So we only focus on task parallelism. More importantly, if you look at many of their scheduling algorithms, they rely on very difficult, complicated data structure that is log-based data structure. For example, OpenMP has implemented a log-based hash table to schedule multiple tasks. The key can be the address of the input and output data of the task and dependency, and the value can be a list of the tasks accessing the input and output data. And when multiple threads try to access or address those informations, and we will run into very frequent access to this log-based data structure. And that will eventually cause a very, very big runtime overhead. Okay. So now I'm going to briefly talk about which is another big part of our system. That's the scheduling challenge that we have overcome over the past few years. As I mentioned, there's a lot of details. I'm not going to talk about those details, but I'm trying to give you a high-level concept about how we overcome the scheduling challenges. So in general, our scheduling algorithm has two parts. Number one is task level scheduling. Number two is worker level scheduling. And the goal of task level scheduling is we are trying to come up with a feasible execution logic, because right now we are not just scheduling a direct acidic graph. We are scheduling a task flow graph that may have iterative cycle, control flow, conditional tasking, and so on and so forth. So we do have a spatialized dependency breaking algorithm that co-design the scheduling with application interface in a way that we can maximize the capability of our programming model without sacrificing too much performance. That is the basic idea behind task level scheduling. Now, when tasks are decided to run by the scheduler. We will move into the worker level scheduling. So this is when we will decide which worker thread to be waken up to run which task, or when there are no tasks available, we will put some of the worker into the sleep, so we don't waste too much resources from the CPU. But the key result over here is we are able to combine this task level scheduling and worker level scheduling into the unified framework, such that we can schedule tasks with in-graph control flow. At the same time, we can maintain a very strong balance between the number of active worker threads and dynamically generated tasks. So that is the part to schedule a static task graph. And to schedule a dynamic task graph, our scheduling algorithm has 3 parts. So first, of course, we'll build a dependency, and then we'll wait for the dependence to finish, and then we will run the task. And there are multiple challenges over here, but basically 3 major challenges we try to overcome is ABA, data race, and synchronization. So ABA means any specified dependent task has to exist correctly. We'll talk about that later briefly. And data race is, of course, multiple thread may simultaneously add or remove successor from a task, because in dynamic task graph programming, everything happens dynamically. And you may have multiple threads trying to add themselves into the success of another task, and so on and so forth. And finally, of course, is synchronization. So first, ABA means every time you specify a task dependency, such as the task B needs to depend on task A over here, the A has to exist correctly. And this happens because when I create first the task A, and it will start running, the runtime will start its execution immediately, right? But at the same time, it may finish real quick, and the operating system will reclaim its resource due to some runtime optimization, memory pool optimization. So next time you want to use the same A again, you want to use the task A again, even though the address, the memory space remains the same, because the operating system try to reuse some of the memory space, but this may not be the task A that you want to use. And this is a very typical ABA problem from operating system design. So to solve this problem, we have a very simple interface that asks application to share a ownership from every task you create from dependent async or silent dependent async. So with this share interface, we actually implement a smart pointer from C++, using C++ smart pointer technique. So we ask application to retain a share ownership for every task that you want to use. In this case, if you want to specify a dependency between task A and task B, we can guarantee that task will exist correctly during the lifetime. So the second challenge is the data race, because multiple threads may simultaneously access the successor of the task. For example, one thread may try to put task B to the successor list of A. Another thread may try to put task C into the successor list of A. Because right now everything happens dynamically, we gotta make sure this simultaneous concurrent access can be protected in an exclusive region without spending too much cost. And basically, the way we handle these challenges, we have a simple atomic synchronization technique, such that we can apply simple compare and swap techniques to enable exclusive access. And as a result, you can construct a task graph by multiple threads, completely thread safe. To handle the synchronization challenges among different tasks because of a dependency, we actually have a very advanced algorithm leveraging the new C++ 20 atomic weight operations. So instead of using a traditional log-based method, we use atomic weight-based solution to largely reduce the synchronization overhead between task execution, executive application. So overall, with all this technique that I just presented, the entire scheduling algorithm in Taskflow is lock-free. There's no lock-based synchronization. So the synchronization cost can be kept very, very, very low. Okay. So that finished the part of the scheduling challenges at a very, very high level explanation. So now I'm going to move on to the experimental result to demonstrate, showcase some of the efficiency of Taskflow from real applications perspective. So the first application to which we have successfully applied Taskflow is VLSI timing analysis. And many of you probably already know static timing analysis, or STA, is a very, very important step in the overall design flow because it verifies the expected timing behavior of your circuit, right? You gotta make sure the signal can arrive on time. So there are a lot of analysis algorithms targeting how I can analyze, for example, the longest path or the shortest path within a given timing budget. So existing static timing analysis, or STA algorithm, typically will levelize the circuit into multiple levels. For example, here I may levelize a very simple circuit of 3 AND gates into 1, 2, 3, 4 levels. And as you can already see, within each level, all the nodes, all the tasks can run in parallel because they have no dependency across different levels. So by levelizing the circuit into multiple levels, we can apply a very simple pipeline parallelization to parallelize the timing propagation across this linearized level. And this is probably one of the widely used methods. It's also implemented in many commercial tools. It's to levelize the circuit and pipeline the propagation for parallelism. But as you can see, if you want to propagate the timing propagation, if you want to parallelize the timing propagation level by level, you end up with many synchronization overhead, right? Because the tasks within the same level that have to run together. You cannot move on to the next level before all the tasks within the same level finishes. But in some case, for example, if these two nodes finish very quick, we can actually move on to this node, right? Without waiting for the other two nodes at the same level to finish. So with Taskflow, we are able to solve this problem by modeling the entire timing propagation more asynchronously, so we can flow the computation naturally with the circuit graph structure. And more importantly, we can also have some in-graph control flow tasks, so we can prove some of the propagation on the fly. And this is something that cannot be done efficiently by existing framework. So based on this idea, we actually propose many new task parallel static timing analysis algorithm. For example, 4 years ago, we have a task parallel static timing analysis algorithm that runs everything on GPU. And later on, we have another GPU acceleration for generating multiple critical paths in a task parallelism framework. And later on, we also expanded to handle the clock network pessimism removal and so on and so forth. So this slide shows you the result of our DAC 21 paper. In this case, we applied Taskflow to accelerate one of the critical component in static timing analysis. That is a path-based analysis on GPU. And as you can see from this table, for large design, we can actually achieve over 600x speed up over one CPU. Of course, if you use a 40 CPU, our speed up is still 44x, which is very promising. So we compare Taskflow with existing system on static timing analysis workload. And as you can see, whether it is runtime, memory, power consumption, or system throughput, Taskflow is always can always give you the best result. And part of this reason, goes to our scheduling algorithm. As I briefly presented before, in our scheduling algorithm is very, very efficient. It's completely log-free. And we do have a very specialized task level and worker level scheduling combined together to optimize your system throughput, latency, and energy efficiency. So far, what we have been demonstrating is based on static task graph parallelism. We model the whole STA timing propagation into a task flow graph. For example, here I may have a simple circuit like this. I have a 1, 2, 3, 4, 5 gates, and I model it as a task flow graph to represent the timing propagations. However, like I said, in many of the STA applications, the task flow graph can be very, 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 very large. It can be up to 10 million or even 500 million tasks. In that case, if we are able to overlap some of the task execution time and test construction time, then the performance gain can be very, very huge. So in this set of experiment, we reformulate the timing propagation algorithm into a dynamic task graph. So we try to find a, so we will model a static task graph parallelism, a task graph from the circuit structure first, and then we will perform a topological sort to find a topological order of the timing propagation task graph, and then we follow that topological order to describe the task graph dynamically. So this slide shows you the runtime comparison between static task graph parallelism and dynamic task graph parallelism when it comes to parallelizing STA. And as you can see from this example, most of the time we are able to speed up the execution a little bit. And for large benchmarks such as VGLCD over here, using dynamic task graph parallelism, DTGP, can actually be much faster than that using STGP, static task graph parallelism. And the reason behind this is the overlap, the ability to overlap task execution and task construction. So here I'm showing you the runtime breakdown of static task graph parallelism when it comes to parallelizing STA in 3 circuit design. So the first circuit design, C1355, is a very small design. It has a 617 tasks, and the second design has over 300K tasks. And the last design, VGLCD, is actually very large. It has approximately 400K tasks. And as you can see from this runtime breakdown, when we increase the circuit size, the time we spend on building the task graph is becoming bigger and bigger. And when it becomes a medium scale, the runtime can take more than 50% of the whole runtime. So this is the slide that compares our implementation with OpenMP. And OpenMP also has a dynamic task graph programming interface. Even though it is more static, but we try to reformulate our timing propagation algorithm using OpenMP's tasking interface. So as you can see from these two line chart, regardless of the number of threads we use to parallelize the timing propagation task flow graph, the task flow based solution is always faster than OpenMP. And both methods approximately saturate at 4 threads, and this is because it really depends on the circuit task graph structure. If your circuit task graph only has 4 tasks that can run independently, then your maximum parallelism will not go beyond 4 threads. But both methods saturate at about 4 threads. So this is a memory comparison between our method and OpenMP. And as you can see again, regardless of the number of threads that you use to parallelize your application, the memory consumption of task flow is usually always much smaller than OpenMP. Hi. So now I'm going to conclude the talk. So first, we express we talk about why it is important to express your parallelism in the right way. And we talk about our motivation and why task-based programming models turns out to be the best approach to scale to the future parallel computer architecture. And then we introduce our Taskflow system, and we talk about how we can use both static task graph parallelism programming model and dynamic task graph parallelism programming models to program a wide range of applications using a very simple graph description language. And then we briefly talk about how we overcame some of the scheduling challenges when we design the system. And then we demonstrate the efficiency of our system using real-world static timing analysis as an example. And Taskflow is an open source project, and it's being used by quite a few people right now. For example, Xilinx is using Taskflow to parallelize their Vivado system. And we also have a module works using Taskflow to parallelize their CAD tool. And we are always very happy to collaborate. And this project has been sponsored by multiple funding agencies. I'm really grateful for that. With that, I'm going to stop here, and I'll be happy to take any questions if you have.
Great, thank you. Yeah, let's open up the questions. I have some, but I'll let the students go first. Sure, yeah, if you want to go ahead.
One slide back, we talked about the percentage, credit percentages of runtime versus build time, the graphs up. I just want to clarify, much to be covered, but did you say the build times as the scale increase, was that linear or exponential, or as the scale for the graph increases? Was it the percentage of the, did you say the build time be greater than percent for large scales? Did you say that was linear or exponential?
So Scott, I will appreciate if you can repeat the question because the
Sure.
microphone doesn't seem to, so I barely hear the questions.
Yeah, I'm also still parsing it. You remember which diagram was? We can go back to the right slide.
It was the second last section, when it's comparing the paragraphs, the runtime versus build time for different
Sure.
runs. As the bigger one, the VGA one, was like a larger percent of the runtime build time. Other than this one. And you said that at the large scales, eventually the build time would be greater than 50%. Was the scaling for the size of the graph linear or especially like how's that relationship for that one?
Okay, yeah. So the question is, yeah, what's the scaling relationship between build time versus runtime as you increase design size?
So normally, the time complexity you spend on building a graph will be linearly proportional to the graph size. And like I say, this is one of the limitation for static task graph parallelism because you always need to construct the task graph first. And keep in mind, that part can only be done by a single thread. Okay? And that is one of the reasons why we are seeing that when we keep increasing the size of the task graph, the time you spend on building the graph time will increase dramatically. But for dynamic task graph parallelism, multiple threads can simultaneously build up the task flow graph. And more importantly, every time you create a task, it can start its execution immediately. So we can overlap the execution time between task graph construction and task graph execution. Did that answer the question? Hopefully.
Yeah, we're getting a thumbs up. Great. Other questions? Okay, last one. So with any parallel scheduling interface, there's always a question of how much overhead it has. It seems like Taskflow is very efficient. Do you have a notion for how big a task should be in order to be, to overcome, For me, the person does graphs only. Would a single vertex be okay to put as a node, or better we have 100 or 1,000 vertices? Have enough work?
So that is a very good question. Because although task graph parallelism has certain advantage, but it also comes with certain overhead. And the overhead to schedule a task in Taskflow, it's about amortized, it's about 800 to 1 microsecond. No, 800 nanosecond to 1 microsecond.
That's quite fast, actually.
Yeah, it's very fast. It's
Yeah.
very fast.
For folks in the room who maybe not know these numbers, you take a out of the box thread barrier on a modern Intel or AMD socket, you're looking at that similar kind of latency, roughly just under microsecond to do a barrier across all cores, which,
Yes.
you know, so that's quite impressive, right? Because yeah, like I said, a barrier you think should be fast. You're not going to DRAM. You just have a bunch of cores talking via L3 cache, but try it out. Go benchmark when you get home. You'll find out it's going to be
Yeah. Usually it's below 1 microsecond. Usually it's below 1 microsecond. Scheduling a task.
Yeah, which is great. That sounds very fast. Do you have another question? Yeah.
Is OpenTimer a consequence of Taskflow, or was Taskflow built for OpenTimer? Because from Taskflow, from what I understood, there's like, it's one of the characteristics you guys tried for was to establish non-diag graphs. And STA are generally diag graphs, from my understanding. So I was like curious, is like,
So Scott, would you like to?
Yeah, I mean, more succinctly, which came first, Taskflow or OpenTimer?
So the whole history is OpenTimer comes first. So when I was doing my PhD at the Bana Champagne, we came up with this OpenTimer, and we realized many of the existing timer, including commercial tool. Because that time I took several internships with the cadence and synopsis, and we realized that this levelization-based approach does have a certain limitation. And then I came back to university. I started to think about whether there can be a better way to parallelize this timing propagation instead of frequently synchronizing your propagation level by level. So then I designed a new way to parallelize the timing propagation. But later on, I realized actually it's very useful for timing application. Why don't we just make it a general purpose task parallel programming system, so we can go beyond STA and go beyond EDA, so we can benefit a broader computing application. And that is the where Taskflow came from. So OpenTimer comes first, and then we have Taskflow. And this is something that I found very, very important because if you look at many of the existing systems, people, when you build a system, it's not building a system based on what you want. You should build a system with the application in mind. You should build a system based on what application need or based on what application want. So I would argue that one of the success of Taskflow is its root in OpenTimer, because it comes from a real world application.
Fantastic. So my questions are kind of following up more about, for a task graph, I think this is fantastic. Sometimes the parallel applications are simpler than that, right? You don't need necessarily to have dependent tasks. So if I want to do parallel 4, I'm sure I could do that with Taskflow. But if you knew you were doing parallel 4, you could probably streamline some things, right? Or what would you say?
So in Taskflow, we also have a parallel primitive for those type of simple parallel algorithms, such as parallel 4, parallel sort, and so on and so forth. But like I say, the biggest strength of Taskflow is the ability to handle irregular application. It's the ability to parallelize irregular application. If your workload is simple parallel 4, you probably won't see too much difference comparing Taskflow with existing system. They are, I would say, they are equally good, equally strong.
Sure. And then there's kind of this in-between area. Maybe you can tell me the name for it, where so there's parallel 4 when you start the for loop, you know how big the for loop is, and then there's effectively parallel 4, but you're generating tasks on the fly. But anytime you generate a new task, it's also, eligible for execution. Does that still apply for that same scenario?
Yes. Okay. That can also be done. That can also be done efficiently using Taskflow.
Sure. And then in a related application, can you do priority scheduling? So like, tasks, rather than depending on each other, give a number. And then they say, hey, I want these tasks to be done in ascending order of numbers or something. So for example, as a graph for something like shortest path, right? I think like Dijkstra, would that be possible for maybe a future framework?
I think they might be possible to build around the dynamic task graph interface we have so far. Because what you want to do is to create a task dependency on the fly, right? So probably there can be a upper level interface or algorithm that can build your idea on top of the dynamic task graph algorithm.
Oh, I see what you're saying. So you have like a priority queue that tells you for a given
Yes,
distance,
yes,
you know who's there, and that way you can feed into dependencies. That makes sense.
yes, yes. And this dependency can totally come on the fly dynamically. So that's the biggest strength of dynamic task graph algorithm.
Very cool. Any more student questions? I have one more nerdy question. Yeah, another student question.
Have you been in talks of maybe like putting this in open road or open lane? It is an open source tool for.
Yeah, that's a great question. So I'll throw in Tsung-Wei. So I don't know if you're familiar, I guess, with open lane, open road. I think they might be even using OpenTimer in Windows, right?
Yeah, I know open road and open lane, yes.
Yeah, so the question is, those algorithms in there probably are open season for parallelizing, right? It might be great for Taskflow.
I think that's totally possible. I think that's totally possible. In fact, I know some of the existing open road project because open road is a very big umbrella project. There's some
Yeah,
several sub projects, and some of the projects such as packaging are using Taskflow already, based on my understanding.
fantastic. Cool. One random question I have, perhaps it's maybe my own biases. So, have you ever compared against or looked into Grand Central Dispatch or GCD,
GCP?
the task framework?
No, I'm not aware of that. But
So
I can look into that.
Yeah, you can. So it's the scenario I was describing where it can't do graphs. It can only do dynamically creating tasks, but parallel for. So that's the one actually that powers your iPhone. So Apple made this many years ago. They got their overhead down to about 12 instructions per task in x86, and then
12 instruction per task. That's really quick.
but like I said, so they wrote it in assembly, and then they wrote it for ARM to run on the iPhone. So on the iPhone, if the app developer did it correctly, when your iPhone's using multiple cores, that's how it's happening. But like I said, it's pure parallel. It's not a task graph. And so yeah, it's out there, and it's kind of a curious thing. I'm always like, because it's so Apple centric, it's not widely analyzed or used, but I'm always curious.
Yeah,
What can
interesting.
we learn from it?
Yeah, this is my first time to hear that.
Well,
I will definitely look into that.
Yeah, it's in the Apple ecosystem, the commercial product. So yeah. Well, cool. Let's thank our speaker one more time. Thanks again for giving this great guest talk.
Thank you guys.
Thank you. I'm gonna stop the recording, but I'll still be on for a second.